As people started using calculus to solve problems in physics and engineering, they started studying more complex situations where they realized that different types of rates of change were coming up in equations that were modeling new types of situations that they had never been able to describe precisely before. So there was this whole new field really of an extension of calculus where you had these equations coming up that involved various types of derivatives, velocities, accelerations, other types of rates of change. You can solve these different types of equations in a lot of different ways. I want to give just a very basic differential equation and solve it using power series. I wish that I was able to do justice to the wide range of situations that differential equations can help people understand, but I really can't do that. Even if I had a long time, I personally couldn't do that for you, but I'm not sure that anyone can in a short amount of time. So here's a very simple example. I'm going to have the equation y prime equals 5 times y, and I'll give an initial value. So what I'm going to be looking for, what this equation will represent, there's some situation, physical, economic, something, where there's a function y, it's a function of some other variable, and the property that I know about this thing is that the rate of change of y with respect to the other variable is equal to 5 times the original function. And I'm going to give another piece of information to help us solve this explicitly. Let's say when the other variable is 0, then the original function is 10. So I want to find a function y that satisfies both of these equations at the same time. This differential equation is so simple that you may be able to guess and check and figure it out fairly quickly. I'm going to use power series just to give you the idea of how you can use power series to attack a problem like this. So I'm going to assume that I can write y as a power series around this initial value x equals 0 or t equals 0. I'll write it, I guess I'll use t. So y is equal to something like bn times t to the n. And what I know about this thing is that if I plug in 0 for t, I should get out 10. That will allow me to solve for one of these constants, b0. And then also, if I take the derivative of this function, this series that I get from that should be equal to 5 times this series. That will give me a relationship between the coefficients, the different coefficients, and I'll sort of be able to recursively figure out the pattern for what these bn's should be. So I think I'll start out by going ahead and plugging in t equals 0. I know when t is 0, y is 10, so that means 10 is equal to, and then this is b0, t to the 0, plus b1, t to the 1, but I'm plugging in t equals 0, plus, and then all the other terms I'll have t's, so when I plug in 0, I'm just getting all zeros. That gives me the first coefficient, the constant term. To get the others, I'm going to take the derivative of this function. Remember, there's a theorem that allows us to take the derivative of the series term by term to pick up the series for y prime. So the constant term will go away when I take the derivative. So I'm going to go ahead and start this at n equals 1. And the pattern we'll just use the power rule. So it'll be, I'll get n times bn t to the n minus 1. Just held the constant bn out in front. And now I want to match up this term with one of these terms according to this equation. To do that, I'm going to rewrite this series so that it's starting at 0. That will just make it a little easier for me to match these up. So I want all the same pieces down here that I have up here, all the same terms. And the first term should be 1 b1 t to the 0. So if n starts at 0, then that first term, instead of an n, it should be n plus 1. So that when I take the first term, it will be 1 like it was here. So this means that for all of my n's, I'm going to replace them with n plus 1. So it'll be n plus 1 times bn plus 1 times t to the n plus 1 minus 1, or t to the n. And if you go through this term by term, you'll see that these two are the same series. So now y prime equals 5 times y tells me that I can match up the nth term here with 5 times the nth term here. And the coefficient of t to the n on each side of the series has to be equal. So here the nth term is n plus 1 bn plus 1 for the coefficient of t to the n. And over here it's 5 times bn. So I know b0 is 10, and then this relationship is going to allow me to find a pattern for all of the other constants in the original power series for y. I'll solve for bn plus 1 here because the next constant I want to solve for is b1, and this equation relates a coefficient to the coefficient that came before it. So if I solve for bn plus 1, I'll be able to get b1 in terms of b0. Just divide by n plus 1, and I'm going to erase this over here so I have more room. If I plug in n equals 0, that allows me to find b1, and I'm just going to start listing out b1 and the others, and I'm going to see if I can get a pattern for them. So I'm not going to simplify things, I'm just going to start writing them out. This is n equals 0, gives me b1 is 5b0. How do I want to write this? I think for the sake of figuring out the pattern, I'm going to write this as 5 over n plus 1 times bn, because I'm thinking that I'm going to start getting fractions, and I want to separate this fraction from that one to find the pattern. So for n equals 0, this says 5 over 1 times b0, which was 10. I'll just write it as 10 over 1. All right. Now for b2, I'm plugging in n equals 1. And that means I've got 5 over 2 times b1. b1 was 5 over 1 times 10. Now I'll keep going. If I plug in n equals 2, I get b3 equals 5 over 3 times b2. And I'm going to start pulling the powers of 5 together, because I see I'm going to pick up a power of 5 each time in the numerator. So b2, I'm going to rewrite that as 5 squared over, and then I also notice I'm getting 2 times 1 times 3. Each time I'm going to be multiplying by the next highest integer. So I can tell I'm going to pick up a factorial in the denominator. So I'll just go ahead and write this 2 times 1 as 2 factorial. And then this 10, I'll just write it as times 10 like that. So what I'm seeing is 5 cubed over 3 factorial times 10. And notice if I do B4, that tells me do 5 over 4 times B3. And if I do 5 over 4 times B3, that will just give me 5 to the 4th over 4 factorial times 10. So I definitely see a pattern here. Looks like if I do Bn, then I should get 5 to the nth power over n factorial times 10. All right, so this works for n greater than 0. And if I plug in n equals 0, that's 1 over 1 times 10. So it actually works for b equals 0 as well. That tells me how to write down the original function y. I'm going to erase this so I have a little more room. So I will update the function y. I know that Bn looks like this. I'll bring the 10 in front, write it on the left side. Starting at n equals 0. That's Bn, and then I have t to the n. And so that is the solution to this differential equation. I've solved it. But for the sake of intuition and possibly working further, I would like to rewrite this as a function that I'm already familiar with, if possible. And it turns out I can do that. I know I can bring this 10 out in front because it doesn't have any n's. It doesn't change as n changes. Bring this constant multiple out in front. And then 5 and t are both raised to the nth power. So I can rewrite this. I'll bring the 10 out in front, and then I have 5t to the n over n factorial. And I recognize this. If I had t to the n over n factorial, or x to the n over n factorial, I recognize that series as e to the x. And if I replace the x with 5 times t, then that just gives me e to the 5t. And then I have 10 out in front. So this is the function 10 times e to the 5t. I can go back and check. If I take the derivative of this, I will just get 10 times e to the 5t times 5 by the chain rule. So that makes this equation satisfied. If I plug in t equals 0, I get 10 times e to the 0, which is 10. That means this is satisfied. So we found the solution.